In Chapter 11, Section 6, we're going to be talking about systems of equations. So in the past, we've solved systems of linear equations by using graphing, substitution, and elimination. We're going to talk about another method, which is using matrices, which is much more efficient. It will also require us to use our graphing calculator quite a bit. So the first thing we want to talk about is a matrix. So a matrix is a rectangular array that can be used to represent a system of linear equations. So each row will represent an equation the matrix will have one column for each variable and one column for the constants. All right. So the easiest way to explain how to turn a system of equations into a matrix is to just do it. So let's go ahead and take a look at example number 1. So according to our definition here, we want to write this as an augmented matrix. And our definition says that we will have one row for each equation. So we have 1, 2 equations, so our matrix is going to have 2 rows. And then we get one column for each variable and one column for our constants. So we're going to have 3 columns. So when we're writing a system of linear equations as an augmented matrix, we always have to have our system in standard form, which means we're going to have all of our variables on the left side, and then on the right side, we're going to have our constants. So in this example, it's already set up this way. So then our columns are going to consist of the coefficients of each of the equations. So 2 and 3. Our next column is going to be the coefficients of our y variables, 3, 2. And then our last column is going to be our constants, 6 and 4. So we don't have to do this, but if you wish, you can label the columns to remind you what they are. And oftentimes, they will put a dashed line where the equal signs go. This is completely optional. Some books do it, some books don't. So it really just depends. But all that does is tell us where the variable ends and the constants begin. But we always know that the last column represents the constants in this situation. So this is our augmented matrix for that system of equations. All right, so let's go ahead and do this. So we're going to have a 3 by 4 matrix for our augmented matrix. our first column is going to be 3, 2, 1. Our second column is going to be 4, negative 1, and 1. Our third column is negative 1, 3, and 5. And our last column is 1, 10, and 0. So that would represent our matrix. So a couple of comments just to make it explicit. So we've been talking about rows and columns. But just to be explicit, the rows are horizontal and the columns are vertical. This augmented matrix actually has, this is talking about the previous example. I'll go ahead and change it since you guys just did this. But it's going to be a 3 by 4 matrix. So the fancy word for the size of a matrix is its order. I'm fine if we just call it size, but if you ever hear the word order, that's what they mean, and it's always rows by columns. All right, so as always, if we can do something forward, we also need to be able to reverse the process. So given a matrix, it represents some system of linear equations. So just like the example you just did, this has 3 rows and 4 columns. So it is a 3 by 4 matrix. So it's going to represent 3 equations in 3 variables, right? Because we get 1 variable for each column, plus our last one is going to be our constant. So if we rewrite this linear system, we will then have x, so 1x plus 0 times y plus 1 times z is equal to 4. We have 0 times x plus 1 times y plus 1 times z is equal to 0. And then lastly, we have 0x plus 0 times y plus 0 times z is equal to 0. Well, 0 times anything is just 0, and 1 times anything is just the anything. So this simplifies down to the following 3 equations. X plus z is equal to 4. Y plus z is equal to 0. And our last one is 0 is equal to 0. So that would be the linear system that is represented by that matrix. All right, so our first equation is going to be 1x plus 0y plus 0z is equal to negative 7. Our second equation is 0x plus 1y plus 0z is equal to 6. And our third equation is 0x plus 0y plus 0z is equal to pi, which then reduces to x equals to negative 7, y equals to 6, and z is equal to pi. So a couple of things we'll notice about the last 2 examples. If there is a 0 for a coefficient, that variable is just not in the equation. So this intermediate step that I've been writing out is not needed. We can just skip directly to this, right? So anything that has zeros for coefficients won't be present. We also notice that this matrix, the way it is written, is very nice because at the end, when we rewrite it as a system of linear equations, x is by itself, y is by itself, and z is by itself. So it tells us x is negative 7, y is 6, and z is pi. In the previous example, that didn't happen. So we're going to spend a little time talking about what each of these are and represent and how that can be helpful. So before we move on, we need a definition. So the main diagonal of a matrix is the elements that are in the same row and column number. So, for example, if I had a 2 by 2 matrix filled with the elements A, B, C, D, A is in row 1, column 1. So it is on the main diagonal. And our element D is also on the main diagonal because it's in row 2, column 2. So it's on the main diagonal. The reason we call it the main diagonal, as you can see visually, is it's the elements that, starting in the upper left-hand corner, are on the diagonal stretching to the other side. So, for instance, if I had the matrix A, B, C, D, E, F, G, H, I, J, K, and L, our main diagonal would be the elements A, F, and K. Because A is in row 1, column 1, F is in row 2, column 2, and K is in row 3, column 3. So the elements on the main diagonal are the ones that are in the same row and same column. All right. So now we want to talk about row echelon form and reduced row echelon form. So a matrix is in row echelon form or REF if the following are true. So 1, the first non-zero entry in each row is 1. The leading one in each row is further left than the leading one in every row below it. And 3, if a row has only 0 entries, it is at the bottom of the matrix. So those are our 3 properties for row echelon form. Well, let's go ahead and leave yourself a little space because we're going to come back and add something else to this chart in just a moment. So leave a little space to come back and add something. So we want to look at our first matrix, and we want to know, is this in row echelon form? So we check our three properties. Is the first non-zero entry of each row a 1? So 1 is check, because the first non-zero entry of each row is a 1. The leading one in each row is further left than the leading one in every row below it. Well, yes, this leading one is further to the left than the other two below it. This leading one is further to the left than the one below it. The last leading one has no ones below it, so that's vacuously true. So 2 checks. And lastly, 3, if a row has only 0 entries, it is at the bottom of the matrix. We have no rows of all zeros, so that is also true. So this matrix is in REF. We look at our second matrix. We do have that our first non-zero entry in each row is 1, but step 2, the leading one in this row has a leading one that is not to the left of it, so it fails. So this one is not REF. And then our last one, our first non-zero entry in each row is a 1. That's good. The one in every row is the leading one in every row is further left than the leading one in every row below it, so 2 is true. And it has no rows of 0, so this one is true as well. So that is in REF. So the next thing we want to take note of is our first three properties to determine if a matrix was in row echelon form had to deal with rows. Reduced row echelon form, or RREF, has these same 3 row properties and 1 column property. So a matrix is in reduced row if it has the above 3 row properties and 4 all entries above or below a leading one are 0. So for a matrix to be in reduced row echelon form, it's going to have all of the 3 previous properties plus this column property that says all the entries above or below a leading one are 0. So first thing, for a matrix to be in RREF, it first of all has to be in REF. So the one in the middle we don't even have to consider. So now we check our column property. So we look at our leading one, everything above or below it is 0. Look at our leading one, everything above or below it is 0. We look at our last leading one, and this one's not 0. So this fails 4. So not RREF. This one we didn't have to check at all because it wasn't REF. Here we check above and below, above and below, above and below. So this one satisfies 4, so it's also in reduced row echelon form. So we'll notice that matrix that's in reduced row echelon form is an awful lot like the U-try you guys just did, where it would tell us X is 3, Y is 4, and Z is 5, right? So reduced row echelon form is nice in that sense. It turns out there's a little bit more we're going to have to take into account when we do this. So let's take a look at example number 4. So we wish to solve the following equation. So the first thing we're going to do is, one, we're going to write the system as an augmented matrix. So 3 equations, 3 variables, and a constant. So that's going to be a 3 by 4 matrix. So we have 1, -2, 3, and 11. Our second row is 4, 2, -3, and 4. And our third row is 3, 3, -1, and 4. So then step 2 is we're going to reduce the matrix to RREF. So to do this, we're going to use our calculator. So to access matrices on our calculator, we're going to need our matrix menu. So there we go. So matrix can be found in the left-hand column. It is the secondary function on our X inverse key. So we go second and matrix. And then the first thing we're going to need to do is edit. So we're going to hit our right arrow and go over twice. If there's things entered in your matrices already, that's fine. You can just edit over them. It's not going to cause any problems. I'm going to choose matrix A. So the first thing we need to do is put in the size of our matrix. So if it was empty like mine was, it's going to default to a 1 by 1 matrix. Well, ours has 3 rows and 4 columns, so I go 3 by 4. And it will then populate a matrix with zeros of the appropriate size. So now I'm just going to type in my matrix. So I hit 1, then enter, -2, then enter, 3, enter, 11, enter. So my first row is done. Just rinse and repeat until I have all of my entries in my matrix. So 3, 3, -1, and 4. So now I'm done. I go second quit to go back to my home screen. I always like to verify that I entered everything into my matrix correct. So I go second matrix. I'm going to choose my matrix A and then just press enter. So it puts it up on the screen, and it does match what it was supposed to. Because the one thing, since our calculator is doing all the work, if we type the matrix in wrong, everything's going to be wrong. So really what we have to do is just make sure that we put it in correct. After that, the calculator is going to do all the heavy lifting for us. So now that our matrix is in there, we want to do some math on our matrix. So we go back into our matrix menu, but this time we're going to right arrow over to math instead of edit. And there's a whole bunch of stuff in here. We want to find RREF, which means we have to hit our down arrow like 12 times. So we go down, we go down, we go down. And we got to be a little careful because we have a false friend. We have REF. We don't want the single REF. We don't want row echelon form. We want reduced row echelon form. So we got to go all the way down to RREF. And then we go second matrix again, select our matrix A, and press enter. After we do that, our calculator converts our matrix to row echelon or reduced row echelon form. So now that we have our matrix in row echelon form, Step 3 is we find the solution. So there's going to be a couple of cases, and it's going to change depending on the output of the matrix. So A, if the main diagonal, if every element on the main diagonal is 1, then the solution is the last column. So we look at our main diagonal for this, 1, 1, 2, 2, 3, 3. So in our case, that's true. So the solution is 3, negative 1, 2. That is x equals 3, y equals negative 1, and z is 2. So this is the best possible outcome. When we get 1s on the main diagonal, everything works out wonderfully. And our solution is the last column in the matrix. So when that happens, everything is wonderful. So the thing that can happen is if every element's not a 1. So if an element on the main diagonal is 0, then two things can happen. So one, the system has no solution, or the other possibility is the system has an infinite number of solutions. So we'll do some examples to illustrate those two cases. So the first thing that we have to keep our eye on is what happened here. If we get 1s along the main diagonal, we're done. We just read off the last column. That's the answer. We love it when that happens. If we have a 0 element on the main diagonal, then we're in this case where it either has no solution or an infinite number of solutions, and we will talk about each of those cases. All right, so let's take a look at our next example. So we're going to go through this same process once again. So we need to put this into our calculator. So equation 1 is row 1, equation 2 is row 2, and equation 3 is row 3. So we go second matrix. I'm going to go over to edit, and once again it's a 3 by 4 matrix, and you can just type over what's in here. So 3, negative 4, negative 1, 6, 2, negative 1, 1, negative 1, 4, negative 7, negative 3, 13. All right. So then I'm just going to check to make sure that I typed it all in correctly. So 3, -4, -1, 6, 2, -1, 1, -1, 4, -7, -3, 13. Good. So now I go second matrix. I go over to RREF under math, so down 12 times. And I select my matrix A, and I get the following. So this time, after I reduce my matrix, we notice something a little bit different happened. So up here, it said if every element on the main diagonal is 1, the answer is the last column. So we look at our main diagonal, 1, 1, 0. So we note the last element is not 0. So 3, and then B, the element in row 3, column 3 is 0. So that tells us that the system has either an infinite number of solutions or no solution. So the way we can tell is when this happens, we write the matrix as a linear system. So our first equation is x plus z is equal to -2. Our second equation, I said z and then wrote y. Our second equation is y plus z equals -3. And our third equation is 0x plus 0y plus 0z, so 0 is equal to 0. So we look at this equation, and it's true. Does 0 equal 0? Sure. So this has an infinite number of solutions. So when the system has an infinite number of solutions, we must parameterize the solution. The column that does not have a leading 1 is the free variable. So in this case, our column that didn't have the leading 1, if we look at our columns, then we have our x, we have our y, and we have our z. So the free variable is z. We solve the non-zero equations for the non-free variable. So we had x plus z equals -2. And we had our other equation is y plus z was equal to -3. So we solved each of these equations for the non-free variable. So I minus z and I minus z, giving me x equals -z take away 2. And then I minus z and I minus z, giving me y equals -z take away 3. Then the solution is x, y, z, but x is this, y is this, and z is free. So then we get our solution then looks like this. We have -z minus 2, because that's our x. We have -z minus 3, because that's our y. And then we have z, because it's free. This is our solution for every value of z. So when we have an equation that's true, we get all real numbers as possible solutions, but we have to quantify that by solving our system for the non-free variables and then substituting them into the ordered triple, and that gives us what our solutions would have to look like. So as an interesting side note, if we take -z minus 2, -z minus 3, and z, we could actually realize this as -z, -z, z, plus -2, -3, 0, or factoring out our z here, -1, -1, 1 times z, plus -2, -3 times 0. So this tells us that all of our solutions have to look like this. So what that means then is that -2, -3, and 0 are going to be a solution. -2, -3, and 0. So -2 would give us -6. -3 would give us plus 12. Oh, it does equal 6, right? So this gives us that solution. But notice something interesting happens if we plug this in. -1, -1, and 1. If I put that into the original equation, I'm going to get -3 plus 4 minus 1. Oh, that's 0. If I plug it into the second one, I get -2 plus 1 plus 1, which is also 0. -4 plus 7 minus 3, which is also 0. When I plug that one in, every single time it gives me 0. Whereas if I plug this other one in, it gives me the constant on the other side. So that tells me any multiple of this would also work. Because if I were to plug in -z, -z, and z into the original equation, I would have 3 times -z minus 4 times -z minus z, which would be -3z plus 4z minus z equals 0z, which is 0, no matter what I pick for z. And that would work in all of the equations. So the idea is This gives us our infinite number of solutions, and it tells us how to find all of them. We start here, and then we add any multiple of this other one to create all possible solutions. All right, so let's go ahead and resolve this. So we want to put it into our calculator. So second matrix, we go over to edit, still a 3 by 4, and we have 3, -4, 2, and 6. We have 1, 2, 3, and 9, and 4, -2, 5, and 0. All right. So then if we reduce our matrix, we end up with the following. So a couple of comments. Oftentimes we'd rather have fractions than decimals. Our calculator's frac function works with matrices. So you can just press math, choose choice number 1 in fraction in case you need fractions, and we get this. So the second thing we want to do is analyze this matrix a bit. So once again, we look at our main diagonal. And we have 1, 1, and then we have 0. So then this tells us that we either have no solution or an infinite number of solutions. And our equations are x plus 8/5 z equals 0. And we have y plus 7/10 z is equal to 0. And our last equation is 0 plus 0 plus 0, so that's 0 equals 1. This is false. 0 does not equal 1, so there's no solution. So when we end up without 1s on the main diagonal, but with a false statement, then the equation, or the system of equations, has no solutions. All right, so let's just kind of go back and recap all that happened. So we write our system as a matrix, we reduce it to RREF, and then we have to check the main diagonal. If every entry on the main diagonal is 1, we're done, and the solution is the last column of the matrix. We like it when that happens. If that doesn't happen, if an element on the main diagonal is 0, then we're in the case where it has no solution or it has an infinite number of solutions. The way that we can tell is if the row is all zeros, or the equation is true, it has an infinite number of solutions, and then we parameterize to find that infinite family. If when we reduce the matrix we have all zeros, but the last one is a 1, that gives us the equation 0 equals 1, which is false, and there's no solution. So those are the 3 possibilities that can happen with a linear system. All right. Well, let's take a look at our last example. So Jude earns a year-end bonus of $5,000 and invests it in 3 one-year investments that pay $243 in simple interest. Part is invested at 3%, 4%, and 6%. There is $1,500 more invested at 6% than 3%. Find the amount invested at each rate. So let's go ahead and write down our variables. So x is what's invested at 3%. Y is what's invested at 4%, and Z, it's what is invested at 6%. So now we need to write down some equations. So we know that Jude has a total of $5,000. So X plus Y plus Z, that's how much he invested at 3, 4, and 6% respectively. So if we add them up, that has to be our total of $5,000. His interest earned, so our simple interest, remember, is P times R times T. So the interest is how much times the rate times the time. So how much he has invested in 3% is going to be his 0.03 is his interest rate times his time, which is 1, times the amount, which is X. Same thing for Y is going to be 0.04 times 1 times Y, plus how much he has at 6% is 0.06 times 1 times Z, and that has to equal his total interest, which is 243. So that gives us two equations, and let's clean that up a little bit. 0.03x plus 0.04y plus 0.06z is equal to 243. The last one says there is 1,500 more invested at 6% than at 3%. So 6% is z and 3% is x. So I'm going to start with a statement I know is not true. Does x equal to z? And the answer is no, right? Because we know one of those has more money in it. So it says there is 1,500 more invested at 6% than 3%. So which is bigger? Is x bigger or is z bigger? Because it says there's 1,500 more invested at 6%, that's our z, than at 3%, that's our x. So which is bigger, z or x? Z, right? Because there's more money invested at 6%. Then to make that equation true, I need to make the left-hand side bigger, because z is bigger than x. So I need to add the $1,500 to this side, because this is smaller than z. Because if x is smaller than z, to make them equal, I would have to make it bigger. And I would make it bigger by adding $1,500 to it. Okay. So now I want to write my matrix, but this is not in standard form. So I need to move some things around. I have x plus 1,500 is equal to z. So I minus 1,500, I minus 1,500, I minus z, and I minus z. So I get x minus z is equal to negative 1,500. So that finally gives me my three equations, 1, 2, and 3. So now at this point, I'm going to put those into my calculator. So second matrix, go over to edit. It is once again a 3x4 matrix, so 1, 1, 1, 5,000, 0.03, 0.04, 0.06, and 243, and then 1, there's no y's, so 0, minus z, negative 1, and negative 1,500. So then I RREF my matrix, and after a moment, it comes up with the following solution. So we get x equals 1,300, y equals 900, and z equals 2800. So this is at 3, 4, and 6. Respectively, right?